Welcome, everybody. Thank you for joining us. Apologies for the slight delayed start. As always, if you're watching live, please feel free to ask any questions along the way. If you think you might like to come on the show yourself, please do get in contact. My details on the channel's About page. There's no show next week due to personal reasons, but on the 22nd of November, I'll be talking to Liz Clark, aka Blitz City DIY. Today's guest, however, is Rachel Mant, aka Dragonmux. Hello, Rachel.
Hello. Good to be
Just
here.
say again, sorry?
Good to be here.
Thank you for joining me. I'm going to hide my face as well, just so it's not too uneven. And would you like to introduce yourself and tell us who you are and what you do?
So, Dragonmux, and I'm a firmware engineer that also does hardware and a variety of smorgasbord of software things and hardware design. Yeah.
Very good, thank you. So
We'll come back to who I work for in a bit, because there's a story there.
That's exciting. So I like to start with sort of how people got to where they are today and what they do, or what they have done in the past. Are you okay to just sort of give us a quick overview of your route to your interests and your hobbies?
Yes. So, started when I was very young, at around 7. Funnily enough, BBC Basic on a RISC-OS desktop.
Okay.
That dates me, I know.
That's fair enough.
But that was where I got my start, and I self-taught, both programming and hardware.
Okay.
But I did end up doing formal education in the form of university. I went to York, in the UK.
Okay.
And did a lot of electronics related stuff and embedded systems related stuff there, including design and build a graphics card for a Spartan 3E starter kit.
Exciting.
That was my thesis project.
So what was the course called, and what was its main focus?
So the course was computer science and software engineering. My specific sub-variant was with a special interest in embedded systems.
Okay.
So that was fun. And it was B-Eng in the end.
Mm-hmm.
Was supposed to be an M-Eng, but complicated reasons that ended up meaning I didn't get to do the master's part of that. But it's what it is.
Never mind.
Yeah. I didn't like any kind of academia by the end of that anyway, so
yeah, it's not for everyone.
No love lost at all. But in the same time frame as I was doing all of this, I also got to do a lot of work for various companies, including a little joint in Swansea, Port Talbot, called Quantum CAD.
Okay.
And so this was to do with...
One second, let me show your screen.
So this was to do with making the firmware for an LED ballast.
Okay.
So this little thing talks DALI, digitally addressable lighting interface, 0 to 10 volts, is mains powered, and can drive up to half a dozen luminaires, they're called. That's the light fittings here, in a commercial setting, which proved to be a really interesting challenge because this thing's driven by a PIC. Running not much faster than the communications protocols.
Oh, okay, interesting.
Yeah, so that was a really nifty piece of programming. I got to do all kinds of like assembly for timing, but the main program's written in C, and making it all fit together really well.
Okay. And I guess with a PIC, it's presumably, I don't know anything about DALI, but presumably it's almost bit banging the protocol to...
It was, because the hardware engineer behind this decided to not put on a DALI transceiver of any kind.
Okay.
DALI, yeah, DALI is Manchester encoded.
Right. I was going to say, is DALI actually a proprietary thing for this manufacturer, or is it a standard in the industry?
It is a standard.
Okay, cool.
It is... 1 second, I have to actually remember the standard's name. It's a really nifty standard. electronics. I have it on disk still, because
Don't worry too
once
much.
you have a document like that, you don't let go of it.
But
Uh,
the idea being that this DALI protocol interface allows you to control the brightness and turn lamps on and off, presumably. Is it kind of
yes, but
addressable
also a
to a
lot
room or
more.
to an individual
All
group?
the way down to an individual luminaire,
Okay, very cool.
an individual ballast.
Yeah.
It allows a lot more than just control over the lighting, though. It has all kinds of extra stuff for doing things like building management system integration. So,
Okay.
for example, there are requests you can make to a ballast to say, "Are you on fire?"
Oh wow.
or "Are you
Healthy
over
or not?
current?"
Yeah.
All kinds
In-
of really cool stuff like that. It's
okay.
BSEN 62386.
There you go. Thank you.
Yeah. Good luck getting a hold of that standard. It's like 250 quid a pop
yeah.
for each section.
Hmm.
And to implement one device, you need at least 3 sections of the
I was going to
standard.
say that the whole paywall for standards thing is a whole other topic that we could get into later.
Oh, yes. It's quite annoying, actually. So this was a nifty project that set me up pretty well, actually,
Okay.
for
And so this was what during uni. This
postgrad.
was a placement or something like that.
Not a placement so much as um, a friend I had at uni knew someone in the company, and they needed a programmer, and they recommended me.
Okay.
So
Awesome.
I was doing professional work on the side of degree. It
Yeah.
was,
Nice.
as you do. Um, but so that actually nicely leads into this was my third year project.
okay. So talk us through this.
It
What are we looking at?
looks really terrible, but what we have on the left here is the starter kit board, with this really big, chunky, high-res header that goes into this secondary board that was the one I designed. So this was my first ever PCB.
Okay.
A little rough around the edges, but we learn. This is
Yeah. Yeah.
why I say on my streams, we all have to start somewhere.
Yeah. No, your first one's not going to be perfect, and
No,
accepting and embracing
absolutely.
that, I think, is it stops that sort of daunting. I don't want to do it if it's not going to be perfect feeling, doesn't it?
Yes,
Yeah.
absolutely. And this thing takes full 24-bit color at 800 by 600 pixels, which is really pushing the FPGA.
Hmm.
Like that FPGA can't go above 100 megahertz. The pixel clock for this ends up being, I think it was 60 megahertz.
Okay. And this is
And
24-bit parallel, was it, from the left-hand side
yeah,
from the FPGA?
plus the horizontal and vertical sync signals and
Yeah.
a couple of other control signals that a framer needs.
Mhm.
And then the framer is then converting the signal into DVI-D, TDMS signaling,
Mhm.
which, funnily enough, also makes the clock rates go up by a factor of 10. So that output is running at 600 megahertz.
Yep.
It's quite something. Um, and this is on a 2-layer homemade PCB.
I was going to say this looks a bit home etched, and is that presumably something that uni had the facilities? They help you through it, and they encourage you to
Yeah,
make your own?
that's
Or?
right.
Yeah.
That's
Okay.
right.
Awesome.
Well, it was also that they didn't have the budget to be able to put this out to a board house, because this was before OSH Park was really a thing.
Yeah, I was going to say this is certainly when I was at uni.
This is 20.
The cheap made up boards is not a thing. It's expensive, wasn't it?
Yeah, it was. This was 2012.
Okay.
So Osh Park was just starting to come into fruition and establish as a thing that existed. And of course, at this point, I had no idea it existed. That took another year or two for me to find out about them.
Yeah.
Such
Okay.
is the way of these things. So yeah, this was a fun board. Also, fun fact: HDMI and DVI-D are identical on the wire.
To some point,
So,
yes.
so you can just replace the
Yeah.
DVI-D port here with a HDMI port, and it will work
Yeah.
perfectly. The only difference is to do with framing.
And audio and things as well.
Well, that's all framing.
Okay, I'll give you that. Very
it's
cool.
to do with what you're doing in the blanking regions.
Yes,
That's the
yeah.
only difference.
Yeah, yeah.
So that's really cool.
Cool. So this was, if you go back to it, sorry, this was a project. Were you doing the gateware as well, or was that something that existed?
Yes.
Okay.
Gateware was something that had to be all done custom, and it was
Yeah.
designed. The gateware was designed so that it could be plonked into a ISE project, plan ahead, and Xilinx Platform Studio with the tools. XPS specifically was the one that they'd teach, so that you could then, as part of the embedded systems module, then actually use this to output graphics onto a screen as part of building like a mini game type thing that
Awesome.
they have you do,
Okay.
or they were planning to have you do in the next year.
Yeah. And this worked as well, which
Yeah.
well, I presume it worked. That's
Yeah,
awesome.
I did. Or mostly. I should actually have dropped the pixel clocks and the display resolution down
Hmm.
a bit because, and I didn't understand this at the time because nobody thought to explain it. Basically, I was accidentally doing a timing violation on the FIFO that was feeding data out to this because the RAM couldn't keep up.
Okay. And did that
So
result in
again,
glitches, or was it just lucky that it worked?
black lines in the output.
Yeah. Okay.
All kinds of black lines all over the place, just constantly moving.
Mostly working, and just
Yeah,
unexplained
yeah.
black lines.
There was also a gateware bug because the
Okay.
gateware was written in VHDL, which
Yep.
was a very smart move on my part for the most part, but timing analysis in VHDL or Verilog even is only so good. And what I really should have done, and I didn't know to do, is basically a formal verification model of this.
Right.
Uh,
Okay.
So, you learn.
Yeah. Awesome.
But it was a really nifty way to be able to learn how to write gateware.
Yeah, absolutely.
I will
I
say.
love video as well because it's so visual. If that it sounds a bit weird to say that, but you
Yeah,
can
no,
see your
absolutely.
mistakes on a screen.
Yes. And like the first gateware I ever wrote was basically an RGB generator,
Mhm.
making the screen do a literal rainbow.
Just a block of red. Yeah. Awesome.
Yeah.
Nice. Cool.
Rotating round through all the colors.
Yeah. Yeah.
It was a little bit more complicated.
Okay. Okay.
Yeah. So that was fun.
Yeah.
After uni, though, is where we start to move into the various professional projects that I got to be involved in. The next major one out the gate was this one, which was done through a company called Newbury Electronics.
Okay. And
I'm
you
gonna
were
skip
employed by
who
them
they-
as
Yeah, I was employed by them as a software engineer in their turnkey solutions department.
okay. Cool.
But I'm going to skip over who Newbury Electronics are somewhat because I don't want to support the company particularly. But this was really cool in that I got to build firmware from scratch for a board that, again, I have no control over the design of. Lots of mains related stuff here, like the devices you see in the bottom of the picture on the right are triacs.
Okay.
So I got to learn how to drive those. That was, yeah. And the processor on this is an ATX Mega, and that will
Okay.
come. We'll come back round to that when we've talked through my current employer.
Okay. Sure.
That comes into future projects,
Nice.
which is really, really cool.
I love
But
learning
yeah,
things
so
in
it's
the
like,
past and then having utility nowadays. Yeah.
yeah,
Great.
exactly. And as well, I used the ATX Mega lineup because of this on MX keyboard, which is something we'll come to shortly.
Okay. Cool.
And this was also first time getting to use these kinds of LCDs and programming graphics and stuff. So this board has a total of 128 kbytes of flash, in which we implement things like full FAT32 file system support, bootloader, all the graphics routines, all the control routines.
All the graphics assets,
etc.
presumably, or have you got fonts here that
But
you're
the
drawing?
graphics assets, unfortunately, had to go on the SD card as
Oh,
another
okay.
128 kilobytes of data. So, yeah, there's some interesting loading stuff happening here. And that's actually what this error during loading's about, because
Okay.
the SD card is slightly pulled out in this screenshot,
Right.
and the board powered on, so it was testing to see that it would correctly fail.
And still do something that user could actually sort of respond to.
Yes.
Yeah. Awesome. Okay. Nice.
So that was fun, and also, yeah, you can see having to do some hellish soldering job to make this work.
Just a few wires there. Yeah.
Yeah. Don't ever have to solder a parallel interface by hand, wire for wire. It sucks. This was caused because the two pinouts are different too.
Right. Okay.
And despite being a board fab house, they didn't want to spin a board to do an adaptation between the two.
Right. That's frustrating.
And they didn't want to respin the hardware because there were some bugs. I mean, there's budge wires, and so they wanted to do one respin only once it all worked.
Okay. Okay.
Which, okay, fair enough, but still.
Yeah.
So yeah, this was an interesting way to break the ice, so to speak. But it didn't last.
Did it feel a little bit like diving in at the deep end, or was it okay?
No, it was okay because I'd already done so much embedded systems programming by this point. I mean, by this point, I had programmed PICs, I'd programmed in Assembly x86.
Okay.
Due to a personal project, I had already programmed in Intel 8051 assembly. I don't recommend that, by the way. And a couple of other things too, which yeah. So and I'd also touched on at this point as well, which was fortuitous for the next company I worked for. Unfortunately, I don't have photos from that company, and I don't think I could show them even if I did. But I then worked for a company called OBR, Olible Racing. I did racing car hardware for about 18 months.
Very cool.
That was cool. I got to play with some very, very expensive boards. I mean, one of the boards, power controller, costs upwards of £1,000 a pop.
Very good. Yeah, I think in the past you mentioned sort of many layers and thick copper and all sorts of things like that.
Yeah, 3-ounce copper board.
Whoa.
16 layers.
Very good. Must be a heavy board, that one.
Very. The power connections on that were done as press fit brass fittings with a grid array of 4x4 thick brass pins that were pushed through the board to make a connection. And that thing could handle upwards of 2 kiloampere.
Wow. Okay.
Cold cranking.
Are we talking? I was going to say, are we talking electric or like electric propulsion, or are we talking sort of starter motors or?
Starter motors,
particular. Okay. But with solid state switching.
Yes.
Yeah.
All solid state. Well, because
Raphael,
it's a
I think.
car.
Raphael, I think we often know better as Perigoso.
Yeah.
Has asked to know more about the project. Is that something you can talk to us about?
Unfortunately, not really.
Okay.
I'm probably still technically bound by NDA for the protocol aspect. But this thing was talked to via CAN. It had a main applications processor on it. It had a supplementary watchdog processor on it. It had 3 different PICs on it, all to do with controlling all the power channels. So each major power channel had its own dedicated microprocessor that the main applications one would talk to.
Interesting. Okay.
So yeah, this was a crazy board to work with. Unfortunately, that was also where I got my loathing of LPC series processors from.
Okay. Right.
I had a very unfun time with 2 LPC processors on that board. One from the LPC 32000 series, and the other from the which series was that? I think it was like the the 57,000 series or something like that.
Mhm.
It was not fun to program those things.
Oh, that's frustrating.
And like a lot of the documentation was outright wrong.
Okay, interesting.
Thanks, NXP.
Yeah.
And when it was right, it was very vague,
I was
or
going to say it's that kind of unhelpful kind of right, where they just give you enough
yeah,
information that you then have to read into it and figure everything out.
or it was doubled down on the fact that the USB controller on that thing, for example, on the main applications processor, was designed to be driven by the Linux kernel. It was designed for you to have memory allocation and memory mapping and all of that stuff, so you could do DMA. There was no non-DMA interface.
Right.
So in order to send or receive anything from via USB, you had to have a working DMA implementation on a processor that had no memory management unit and could not do allocation.
Yeah.
So yeah, that was headaches abounding. But unfortunately, good things don't always last, and that company stopped paying me.
Right.
So I ended up then going to old day job after some time, and like in between all of this, I was doing personal projects. Like this, for example, was designing and building a 30 watt a channel dummy load, also based around a PIC, funnily enough. As you could probably tell, I like PICs. That they have their uses. They're very good as what their original name implies, which is peripheral control. Peripheral interface controller is what PIC used to stand for.
Yeah.
So yeah, if you're just bapping some peripherals, that it's perfect.
Yeah.
And also around this time, I did a redo of that third-year project from uni.
Much tidier.
Yes, as you can see, I learned a lot. So this is a HDMI port, but it's still the same DVI-D signal technically, and the same framer. But this is designed to fit onto the bottom of a paralleller, the single board computer. Which, entertaining fun fact, those connectors are from Samtec.
Yeah.
And they cost like 20 quid a pop or some ridiculous amount. It was nuts trying to get a hold of those. I ended up managing to persuade Samtec to send 5 engineering samples out.
I promise I'll buy 10,000 soon. No comment.
Something like that.
Yeah.
And it got me through it. It got the project to work, and
nice. Very good.
Well,
and this one, if I dare say, has no bodge wires.
Correct. This has no bodge wires. Hand soldered, and yes, those are QFN packages. You can solder them without a hot air gun.
Very good. Well done.
The trick is to put a pad on the bottom side with thermal wires going through the board that you can then allow solder to wick through. Apply flux on the top side, put your chip down, tap a couple of pads on either side, and then heat with the board held from the bottom with solder on the bottom or on your iron and a good amount of flux, and the solder will just wick through, and that will do the thermal pad on the bottom. Will also self-center the part if you've got any slight misalignment, and then you can solder the pins on the outside as normal.
Magic.
Yeah.
Good technique. Well done.
Yeah. So, and this was kind of where we mastered that.
We've got Aki bragging about how many Samtec samples they. Oh dear.
Oh yeah.
Hi Aki.
And yeah, it was Gavin Noob, a very thick board. Yeah. So, and this at the time was my setup. It was comfortable.
Very nice, yeah.
Yeah.
Cool.
So,
how did you find 6 screens?
Very, very useful, especially as like this was early days of streaming. I think, yeah, this was early days of streaming. Um, and so you've got OBS and stream control, and then the bit I'm streaming out, chat,
Yeah.
and then any extra additional information I need
Nice.
on the upper screens. And that one because paralleler, but it wasn't powered on at the time.
Okay.
Yeah.
Very good. I've seen a lot of people saying things like, how can you possibly need more than one screen? And for someone like me in particular, who's got very poor working memory, I can't manage on one screen. And so it's nice to see
Likewise.
not everyone agrees with these people.
Yeah, no, likewise, and as well with this, like trying to stream on one screen,
Oh,
you
absolutely,
can't,
yeah.
because you need to be able to see chat to moderate it. You need to be able to see OBS to be able to change scenes.
Yeah,
You need to
absolutely.
be able to control music in the background and that kind of thing. It's just not manageable on one screen. So yeah,
Very
that's
cool.
the reason. Um, After all of that fun stuff, though, I ended up having this dry period for a few years, around about 4 or 5 years, because unfortunately, with old day job, my work-life balance was atrocious.
Right. Was this a
Uh,
matter of you got into the office on time in inverted commas and then just worked until everyone went home trying to work and then maybe carried on a bit, or what was going on there?
well, so part of it was because the working hours of that company were it was a 9-day fortnight, 9.25 hours a day,
Wow. Okay.
for Monday to Friday on the first week and Monday to Thursday on the second week, except on the first week Friday you got 8 hours, and on the second week Friday you got the day off. It was
That
free for
sounds
you to do whatever you wanted.
mighty complex.
Yes, and no.
Okay.
You get used to that. It's just something where it becomes you, instead of doing a weekly cycle, you're doing a fortnightly cycle.
And is that kind of
That's it.
shift and responsibilities related, or is that just how they worked?
Um,
Whole
it
office did the
was
same thing, kind of thing.
it was because of other parts of the company that we can't really talk about,
Yeah, sure.
unfortunately. But everybody across the entire company was because of this forced to work this 9-day fortnight.
Interesting. Okay.
So that everybody was always in or not in at the same time. Uh, I did have some fairly good flexibility on when I could get into the office by. It was in by 10. Starting from about 7 in the morning was when you could show up. And out by 7 p.m.
Right. Okay.
But when you're doing an 8.25 hour day, you just don't want to know when you get home. It is so draining. I cannot stress how draining versus a normal 9 till 5 that is. Especially as that also includes a half-hour unpaid lunch break
Right. Yeah. Okay.
that you had to take. So even if you did work through lunch, you still had to do the extra half. You still had to do an extra half hour.
Yeah. Okay.
Yeah. So that was part of why.
So you were there for, was it 4 or 5 years? Did you say?
5 years in the end.
5 years. Okay.
But
And
luckily, that work-life balance stuff all changed with the pandemic.
there you go. Okay. Cool. So it had its positives.
Yeah, it did. It caused me, after a couple of months of the lockdowns and all of that stuff. Once things had calmed down a bit, and I'd started watching Esden by this point, which we'll come back round to because that was fortuitous.
Okay.
I ended up starting to stream as well. And one of the first projects that I did with those streams was this, which is SpyFlash Programmer, which is this little dongle, not that much bigger actually than Blackmagic Probe, which is why it ended up being fortuitous about Esden.
Okay. Hinting at a lot here. We'll come on to it, I'm sure.
Yes, we will. And this is a dongle designed for programming SpyFlash, obviously, but with controls for a reset line for a target. So, for example, if you're trying to reprogram an FPGA's associated SpyFlash for the bit stream, you can hold that FPGA and reset, and for the vast majority of FPGAs, that makes the FPGA release the spy lines. It stops driving them. So now you can take control and do what you want to the flash. And that actually turns out to be really, really useful.
Yeah.
This is using a TIVA-C, which is a non-microprocessor from TI.
Yep.
And can reprogram large flash chips in a matter of seconds, despite being over USB full speed.
Okay. I was going to ask actually, because I think I was aware of this when you started the project. And at one point, I think you mentioned that there was going to be flash on board, so you didn't even need a host computer. Is that the case? Yeah. Okay.
Yes, there is. I think one of the later photos we've got actually shows the rear of the board, and you can see on that there are 2 flash chips, and that's actually what these 2 buttons are for.
Right.
Unfortunately, that feature hasn't yet been implemented in the firmware. I've got to go back around to the firmware and actually do that.
Okay.
But it allows you to power the board up and press one of those buttons, and whatever's in the associated flash chip will then be dumped out over the SPI bus, and reprogram your target.
Awesome.
So you can use this in a production setting, which is quite nice. That Blackmagic probe I bought with my own money.
Okay.
Unlike the rest of them. But this was how I was able to program. This was how I was able to program SPI Flash Programmer. This was my first foray into Blackmagic Probe, which, gosh, it's so nice. But we'll come to that. And there you go. There's the flash chips on the back.
Okay. Very good.
And probably too many capacitors, but it works. So I'm not going to remove any of them.
Fair enough. Looking good. I like the labels as well. That's something that for this kind of thing is so important, and often gets missed or hidden away in a document somewhere or
yeah, it's really, really handy too. The number of times I've had to sit there with a schematic open for the board I want to connect to, and I've then used that to go, okay, so it's that cable there and that. So good. I am very glad I put the time into add that.
Yeah, awesome. In terms of that pinout, is that something that you did a bit of research and found that people were using? Was that an 8-pin connector with this particular pinout, or was it just something that you went for?
We couldn't find a pinout that anybody was using, so we designed our own for this board. And it's designed so that if you rotate it through 180 degrees and plug it in, no damage can occur.
Oh, shiny.
You'll notice, like, for example, the VCC here maps to the no connect.
Yeah, very good.
The ground maps to peripheral input.
Yeah.
So
nice.
You end up not being able to damage anything, and that's, yeah.
I approve. Well done.
Yeah. No, I was pretty proud about that.
Another comment from Aki. More caps, please.
Oh, she would say that. I mean, I count them up though. There's a lot of capacitors on the backside of this board. Over 18 of them. It doesn't need more.
Anyway, sorry. Let's stop derailing you.
The other project that at the same time was MX Keyboard, this is a half-assembled first generation of that project. And this came about because I wanted a keyboard that had full RGB backlighting, but no flicker, because we're very sensitive to flicker. Like with mains lighting, for example, particularly when we're tired, we can see it flickering on and off very, very slightly, and that gives us headaches. So.
I can relate to that. I'm sorry you struggle. Yeah, it's a tricky one.
Yeah. So hence this project was born, especially as like, if you've ever looked at tech videos of keyboards, a lot of the times, like you'll see them twinkling in the background from the flicker, or someone will run their hand over and you can see the flicker as they do so, and you're just like, oh.
Oh dear.
This doesn't have that problem.
So is there anything in particular you did to address that as a feature or a requirement?
Every single LED is directly driven by a driver, which is a 12-bit, 400 kilohertz pulse width modulation driver.
Okay.
The 24 channeler driver. So you've got R, G, and B drivers, and then each one of those fans out. The same pin goes to all three go to one LED.
Got you.
And
Okay.
there you go.
And the result there is that you're not scanning the keyboard and doing some kind of matrix operation. You're actually directly one-to-one. Yep.
That's right. And
Brilliant.
that also allows us some really nice backlighting stuff where, like, because they're SPI connected, the ATX Mega on this board, told you would come back around to that one, is able to do DMA across the chain. So you can set up a chunk of memory with the RGB color data, tell the DMA controller, 3 channels of the DMA controller, here's the data, put it out to that register, please, for each of the 3 channels, and there you go, there's a backlighting.
Great. Cool.
Which happens to mean that this can hit 60 frames a second. It's basically a screen.
Dare I ask about Apple?
Haven't tried that yet, but we should. You're right, we should. It's a very low-res screen, though, to be fair.
Oh, that's okay. Just out of focus, it'll be fine.
Yeah. And the other fun part with this project is, guess how many layers this keyboard board has?
Oh. I'm going to go for 6. Hey.
Yeah.
It's, I can see why, though, with all of those. Yeah. Anyway.
And have a nice beauty shot of it. Like, this was something where Osh Park were just about to start doing their 6-layer service, and they were like, we need designs. Someone?
Okay. Someone test.
Yeah, so like, well, we've got nothing to lose.
Yeah. And they accepted and did one for you? Yeah. Awesome.
And it is really nice. Like the 6-layer process from Osh Park is so nice. You can see it too in the silk screen and everything. Like, so nice.
Very good.
So, yeah. That was a couple of revisions, and I've been streaming all of this throughout the pandemic.
I was going to ask, actually, when you first mentioned streaming, I don't know if it's true, but do you find sort of a sense of community doing a project with others? And it's kind of more enjoyable and it keeps you going, in inverted commas? Is that ring through for you?
So the original reason that we started streaming was because of that no personal projects getting done problem, and it really hurting our mental health. So it was like I wonder if this could be used as a way to force us to do projects. And
less force, more give motivation. Is that right?
Well, yeah, okay. And basically use it as a way as well to see how well we were doing and get feedback and also teach. Because, there's a long time of experience there, as hopefully shown, and we wanted to be able to share that. There's no point gaining a whole load of experience if you keep it all to yourself. There's no point, in our opinion at least, learning how to do all of these things that aren't necessarily well documented or are not well explained if you're going to keep it all to yourself. Like, that's
I really appreciate the community that I've found myself in more recently, where it's so open and willing to share, and it's very different to what I was doing previously, where it was very closed off, and a design would appear and what goes into it is quite secret almost. Yeah,
which that's no fun.
No,
I want to know what's going on.
Share. Brilliant.
So,
okay.
Then we get to much more the present, the last year or so. as you probably are aware, and as other people in the community are probably aware, uh, I've been trying to emigrate to the States for the last year.
Hmm.
Immigrate rather, and in that process, I ended up managing to spend 6 months over there with my wife Aki, and got to learn how to do solder paste based assembly. This was the first ever time I'd done that. This is
Okay,
Glasgow.
awesome.
Um, this was also the first time doing 0402, which
Hmm.
is difficult for me because I have a tremor.
Right.
So trying to hold the hand still, and get the placement is supremely painful.
Yeah. How did you find it?
Actually not too bad. Once I got a technique down for how to do 0402
Hmm.
and had understood the mechanics of trying to pick up really big packages like BGA and high pin count QFN with
Hmm.
tweezers, which I hadn't really had to do before with any precision,
Hmm.
um, then yeah, it's quite reasonable to do, especially if you've got a decent toaster oven. Like, people find this scary, and really, I think, is all in their heads. It's a mentality thing.
So for me, certainly when I was starting out, I don't know if this rings true for you again, but
Yeah.
I've always had this sort of issue with consumables and making use of things which can't then be used again. And so if I give something a go and it doesn't go to plan, then I feel like extra negative about what I've just done. The fact that I've just wasted, for want of a better word, this stuff, this time. And
Sure.
and with
I
software, that's not
guess.
really a thing, but with hardware, that's much more of a thing.
I guess from that perspective, I've always found. Um, I think because I've had to learn how to do the desoldering aspect of things as well, and how to bodge and fix,
Hmm.
at least for not PGA things, I'm like, oh, okay, I've got a solder bridge there, I can fix that with my iron.
Yeah.
Or,
Okay.
oh, that part tombstone, oh, I can fix that with my iron.
That's nice to
So,
hear. Yeah.
yeah, I think from that perspective, and that's the thing, I really encourage people, do try, and you will occasionally fail, but that itself is a learning opportunity.
I was going to say, there's a lot of learning that goes into this. You can't just immediately
Yes.
hit the ground running. That's not how it works.
No, no, no,
Yeah.
indeed. I mean, that first board you saw, I didn't do very much of the soldering on that. I could solder back then,
Hmm.
but I wasn't allowed by the uni to
Oh
do
wow.
like assembly of the TQFP. I wasn't allowed to do that. I could solder in the connectors,
Okay. Interesting.
but yeah, the surface mount part was done for me. I'm like, oh, okay.
No.
I wanted to try that. um, so yeah,
Okay.
and like, I didn't show it, but the first few times I did surface mount, like the first time I did surface mount QFN, because I got the pads wrong in the board setup,
Hmm. Hmm.
I butchered that board.
Right.
Like, there was no solder mask left. The connections were terrible. We burned the chip
Oof.
slightly,
Okay.
which is impressive to do on a temperature-controlled iron.
Yeah.
Um,
Well done, I suppose.
yeah, oopsie. So, and now we're into our modern PCB design. So, thanks to Stream, we were able to do this Project Mithra. This
I
is a
heard about
all
this and never
USB-C.
saw the results. I'm excited.
Yeah, this is an all USB-C uh, USB hub that does power delivery on every single downstream facing port, which is
I
why
was,
the really chunky power supply here.
I was going to ask if those LEDs were indicating the voltage.
It indicates a few things.
Okay.
One of the LEDs is an error indicator, one is a power delivery negotiation indicator, and the other one's a speed indicator.
Okay. Okay.
I think the other one's a
Awesome.
speed indicator. But anyway, yeah, you get the idea.
Yeah.
And this is another 6-layer board, and so you can see become a lot more comfortable in board design, and it's taken years. We've just
Mhm.
chronicled about 10 years. So when people are like, "Oh, but I'm never gonna be so as good as you," it's like, no, you will.
Yeah, it's not
Well,
overnight, but yes, you'll get there.
yeah. I mean, I started from trash.
Sorry, we've got Aki taking claim for more capacitors again.
Well, yes, she encouraged the. I'll go back to it. She encouraged these two giant Kemet caps.
Very
Um,
good.
so yeah, she is indeed to blame for uh, 47 microfarad of capacitance on V-bus and another 47 microfarad on the input to the power supplies,
Yeah.
which is nuts because these things, this can deliver 40 watts a channel
Okay.
for a
Very good.
total with two boards in one hub of 320 watts delivered.
It's fairly chunky.
Yeah. Uh, I had fun designing this, as you can
Mm,
probably tell.
yeah.
Um, and this was also assembled again using a paste mask and hand placing all the parts and then
Okay.
putting it in a reflow oven.
Awesome.
Um, and other projects that I've done on stream is this headphone amplifier. So, and this also allowed gateware. So one of the things that streaming allowed me to pick back up because I hadn't done it since uni, in fact, was gateware.
Hmm.
Uh, because I got to find out about the open tools, thanks to Esden, and play with them due to his streams, and then finding out about Amaranth. And so now I've got this body of projects which include Amaranth Gateware, open source hardware built in KiCad, and this project was particularly interesting as it was the first time having to do 3D design
Hmm.
to fit a chassis in in concert with doing the board design.
Okay.
Uh, so you can see, for example, these rails on the board, um, and then standoffs on the other side. And the rails and the standoffs together form retention for the board to hold it in 3D space,
Hmm.
which was,
Very
yeah,
good. Look at that. Nice.
yeah. And now you can see Spy Flash Programmer in use. This is
Oh,
like
awesome.
the the primo way to use it. There's a connector on the backside of that FPGA board, which is the audio interface board,
Yeah.
round about here. And that allows the access to the Spy Flash that the ICE40 here uses for configuration. This is an ICE40 HX8K, um, which very nice FPGA, and that allowed me to program without any proprietary tools, any extra expense.
I was gonna say you got so much open tooling here that it's just fantastic
Yeah,
to see
yeah,
people
yeah.
doing
It's like
things like
SciFlash Programmer is fully open,
yeah.
which so you can go clone the repository, compile the software, compile the firmware, make one of these,
Hmm.
assemble it. The bill of materials is out there, and have your own if you
Awesome.
really, really want. Um, there are a couple of hardware bugs in that revision, unfortunately. Like, for example, the logic level translator, this chip right here, can't actually be powered down, so you can't drop off the SPI bus, so the resetting doesn't quite work right.
Okay.
That has been addressed, though. There's an
Right.
output enable that we missed that we just put ground.
Yeah.
Um,
Nice.
that was
So talk
fun.
to us more about this headphone amp. What was the sort of the goal there? Is it Class D amplifiers and sort of the best you could
Um,
do, or what's going on there?
no, it's Class A actually.
Okay. Okay.
It's so the headphone amp main is built around the Objective 2, which was designed by Northwest AV guy back in 2011.
Hmm.
Which you can just about see under here. There's the preamp there, the two output amplifiers, um, 10k ohm logarithmic trim pot
Hmm.
for a hardware volume control, Signal in, signal out to headphones. Preamplification selector that basically changes some resistors that go into that preamp. And the goal there was we wanted a decent headphone amplifier, because trying to drive the cans that we run is quite difficult. And at the same time realizing, hey, we've just done the surface mount version of the Objective 2, halving the amount of board space it takes. I wonder if we can also put a really high quality DAC on here. And it turns out you can.
Awesome.
So underneath this board is a 24-bit DAC that has a minus 123 decibel noise floor, which is very quiet. And the idea is to try and keep the noise floor below minus 120 decibels. So we've got just 3 decibels of noise floor to play with, which means that thermal noise factors in. And that then goes out into a pair of twisted pair, actually coaxial in the revised design, wires that then wire over to the signal routed board here, which is basically built around a latching relay. And that's where the FPGA comes in. We needed a way to drive the DAC, and well, the 2 easiest ways to do that for high def sound is USB, which is also how you power this thing, and SPDIF.
Nice. Okay.
So you've got an optical input and a USB input going through a high-speed USB PHY into the FPGA, clock generation for the DAC, and then the resulting I2S and SPI signals go out over a ribbon cable onto the board under, through opto isolation into the DAC, and there you go.
Very cool.
The opto isolation is so that we don't contaminate the digital. The digital plane on the FPGA board's quite noisy in audio terms, so we didn't want that going through into the audio sections in any capacity. That's why the opto isolation.
Okay, awesome.
So, and yeah, this is all assembled again using that same paste. This board was all done using paste, and then the other 2 boards were assembled by iron.
Okay.
So.
Yeah, brilliant.
Yeah, lots of fun.
Good job. Is that now a thing that you use, the headphone amp? Is it operational?
Unfortunately, thanks to the parts shortage.
Okay.
On 2 parts, I think it is.
Right.
And unfortunately, the parts are now in the States while I'm here with it. So final assembly is going to have to wait until whenever we get to go back into the States, which is a whole nightmare in its own right.
Yeah, I'm sorry about that.
Yeah, so am I. The other project, though, that all of this spawned is a power supply for Mithra. 320 watts is a lot of power. So future projects, that is the power supply, the mains power supply's filter inductor, which size comparison against a USB-C port.
Nice and chunky.
It has to be able to handle all of the current for 24 volts and 320 watts with a margin for error. So that's some chunky copper.
Nice.
But all of this ended up being very, very fortuitous. All the streaming ended up being very, very fortuitous because it ended up giving us an out for old day job.
Okay, cool.
And that came along in the form of 1-bit squared, Esden. And now the lead developer for Blackmagic Probe.
Awesome. Congratulations.
Thank you.
When did that happen? Is it a couple months ago, I think? Or
no, the actual One Bit Squared took maintainership about a year ago at this point.
Okay.
It was when I went to the States, was me, I'd just quit the old job
Right.
and started to do work for Esden, for One Bit Squared.
Hmm.
And it was a little slow to start with. I mean, these things often are. It took a little while to really take control of the project and assess the state of everything.
Hmm.
And it's taken a whole year to really get it to a maintainable point, which is kind of scary. In fact, I'm still working on that maintainability aspect. I mean, I still got. This has been my work for the last month and a half. Has been all of these cleanup commits,
Wow, I hadn't appreciated this. Well done.
and it
That's
goes and it
that's a big job.
goes
Yeah.
all, all the way back to uh, beginning of October, end of September
Yeah.
was the first cleanup commits here.
Okay.
Uh, and trying to make this PRable at the moment. So this is what your money goes to when you buy a Blackmagic probe, really.
Keeping the project alive. Well done.
Yeah.
Okay, so you're now working with or for One Bit Squared? Are you specifically on Blackmagic,
Um,
or are you?
so I am currently specifically on Blackmagic, but my involvement in the company will be much more broad once I'm back in the States.
Okay.
The idea, for example, being an extra pair of hands to help with the pick and place machines and keep those maintained.
Okay.
Um,
So you'll
so
be
there will be
physically close to Esden, which is nice.
yeah, that's right.
Yeah. Awesome. Oh, that's really good.
Yeah,
Again,
just
sorry.
about 500 odd commits or so. Actually, it's about 170 commits before fixing how it was all sorted. It's now around about 250 commits cleanup that need pull requesting. I am so sorry, Heston.
Yeah, who wants to review that? Anyone?
Well, especially because the first chunk of commits are all Clang format.
Right.
So it's a lot of churn,
Mm.
and it's all non-functional churn.
Right. Okay.
He still has to go through it all to make sure it all makes some sense.
Yeah. Yeah. Ouchies.
Well, I mean, regressions have been a thing. It's just generally speaking, the community's been very good at letting us know before a release has been made with the
Yeah.
regression in. And actually, that's an interesting point. I've been able to apply all of this time spent learning embedded systems and electronics and all of this time writing firmware in a really nifty capacity on that score, because as actually Anti's been helping with, we've done a lot of cleanup to do with how Blackmagic Pro bit bangs SWD, because
Mhm.
many people aren't necessarily aware of this, but Blackmagic Probe does not have the ability to talk those protocols in hardware. It has to bit bang all of them.
Yep.
And the routines for those were doing a timing violation, specifically a setup and hold violation, which was why people were like, it works on my parts, it doesn't work on mine. Like,
Yeah.
why is this flaky?
Well, yeah, much appreciated for your input on my issue a little while back. So thank you.
Yeah, well, no, you
Um,
highlighted a really great bit of timing that was still wrong with the SWD cleanup that we did, the serial wire debug cleanup that we did.
Yeah.
So, and this is why I said the community's been instrumental in not making quite as many regressions as we'd otherwise have happen.
Mm-hmm.
Because we had, over the course of a couple of months, I think it was about half a dozen people all tested that one pull request. Actually,
Oh wow. Okay.
probably more than that. It was probably more like a dozen people all tested that one pull
Yeah.
request, and I had bug reports coming in DMs in the Blackmagic
Oh no.
Discord channel, on the ticket, And that's fine, because it meant we found regressions before they became actual regressions. And the patch that got merged was significantly better than the original patch.
Yeah.
So I can't complain as a maintainer. That's like ideal,
Much
because
better to have tested the PR rather than the post-merged
yeah,
issues appear from
especially
nowhere. Yeah.
because Eston's not able to give all of his time to the project like I am. Um, he can only test pull requests that we open
Yeah. Yeah.
every so often. So that's why you've seen, like, I'm nice and responsive as best I can be for pull requests that are opened by other people, but mine stick around on the tracker for ages because I'm not the bottleneck. Eston is.
Right. Right.
And actually, that's something Eston really appreciates in my involvement in the project. That's like, yes, I like this.
Great.
So
Very good. Cool.
hopefully
So
we'll get to do the release for V1.9 soon.
fingers crossed. Yeah.
I would love it to be done for Christmas, really.
Nice. Nice.
Because then we can move on to more interesting things, because there's this lovely body of targets that we've got to implement support for still, including ATX Mega,
Okay.
because we're adding support for JTAG PDI to the project. That will be in V2. And then there's also things like the IMX real-time stuff, the IMX RT boards.
Yeah.
Those are having support added in V1.10. We've got to do that.
Okay.
That's going to be
Yeah.
fun.
So these are all pipeline tasks for you to get on with, but not yet. And you're sort of waiting for them to come up. Is that right?
The pipeline tasks that are stuck behind the cleanup.
Yeah. Okay. Okay.
Yes. There's also things like a RISC-V support. It will be inbound for V2.
Awesome.
So
I know you've got a lot of targets already in the project. Is is Flash
yeah,
and space and everything? Is that becoming an issue, or are you actually managing okay?
Well, that's actually one of the things that the V2 firmware should help address. Um, I mean, this version, V1.9, is actually smaller than V1.8.2,
Okay. Cool.
despite having support for more targets.
Oh, even better. Well done.
And that's actually because of all the cleanup that's been going on. Small space savings here and there of like 8 bytes here, 8 bytes there, it adds up.
Yep.
But also, Curiad was also working on this firmware as well, and the Cortex-M support used to have this giant chunk of XML stuck in the firmware blob.
No. Really?
Yes, because that's how GDB learns about targets, is you have to
Oh,
give
I
it an
see.
XML description.
Okay.
And rather than having this baked XML blob, she was able to rework that code, and it is now this generative thing that builds a buffer in memory in real time, at runtime.
Yeah.
So we only have to have small fragments, and this saved something like 200 bytes.
Nice. Okay. Very cool.
So code smarter, not harder, or something.
And I think that's a good example of not optimizing until it's actually important as well. Because a blob of XML does the job, but now that you're running out of space, actually you maybe want or need to do something different.
To a point, one of the problems that the codebase has had for some time, though, is how certain things are written. For example, a target flash routine would traditionally have been written as this while loop that disguises a for loop,
Right.
which is doing iteration backwards. In actual fact, a good example of this is in the I think actually in something like the STM32G0 support here, if we go down to the flash routines, oh no, that one's already had our tend administrations applied to it. That was a bad example.
Don't worry too much, but feel free
Mm,
to talk about the concepts if you can.
It's better to do this with a visual example because
Okay,
it's
all
a
right.
really weird way of writing loops,
Okay,
and it hurts code gen because the compiler can't see through it for you.
right.
The compiler has to do the dumb thing when it really wants to do a smarter thing. Here we go. Yes.
Do you
So
mind just
here's
making
an
it a bit bigger for
example.
us?
Yeah, we can do.
Thank you.
So you've got a length coming into this function which is not const, and this while loop. But this while loop's actually a for loop. And at the end of the while loop, there's this chunk of logic that has to be done to correctly decrement the length parameter. And it turns out that all of that is really pessimistic,
Mm.
not to mention way harder to read and understand,
Yeah,
and
okay.
harder to keep correct over time. When people change the code and you don't realize what this is doing, the so one of the cleanups that we've been having to do is slowly pivoting all of these to a for loop with an offset, so an extra local. But in doing that, the compiler is able to put that in a register,
Hmm.
and then because we don't have that if block at the end, instead it's just offset plus equals block size, which is much simpler, obviously.
No.
Um, the compiler is then able to do a much better job at optimizing this code,
Okay.
which is
Interesting.
nice.
Yeah. Very cool.
So it's stuff like this that's been plaguing the project and
Yeah.
causing a lot of problems. Um,
But you're on
like
top of
I,
it, and it's going well, which is awesome.
yeah, yes, indeed.
Yeah. Well done. Very good. I think we're about sort of to the end of the stream now. Is there anything in particular you'd like to talk about or shout out about before we say goodbye?
Um, very good question. I guess one thing to say is if people have targets that they would like supported by Blackmagic Probe that are not currently supported, even if they are not ARM targets, do open issue tickets.
Hmm.
It is welcome. As mentioned, we are introducing, for example, RISC-V support. Initially, that support will be for RISC-V debug version 0.13, but it is now, due to someone doing this, on the docket that we have to go and support, pardon me, that we have to go and support V1 as well, because
Hmm.
there will be a piece of silicon released late next year that supports the V1 protocol, so we have to implement that.
Okay.
Um, and at some point, we also want to go back and try and figure out how to support the 0.11 protocol, so we can support Sci5 silicon,
Right. Awesome.
which is going to be difficult. But like that's kind of the point of buy real Blackmagic probes. It pays for the dev,
Yeah.
and open issue tickets for support for targets that aren't currently supported, because more
Help it
likely
grow.
than not, we just don't know that people want it supported.
Yeah. Yeah. Very cool.
And like get in contact to send boards or what have you. Likewise, people can support us through a sponsorship link on GitHub,
Hmm.
and other various things like that. So we can see here on GitHub, there's a sponsor this project. That really helps.
And you mentioned purchasing a Blackmagic probe. That's from the One Bit
Yeah,
Squared store. Is there anywhere else we can
that's
get them?
right. At the moment, no.
Okay.
Um, but Aston is going to be looking when he gets a chance at throwing One Bit Squared on Amazon.
Okay.
Um, oh, I lie slightly. You can also get one bit squared boards through Adafruit, so
Ah,
you can
cool.
get that
Okay.
Magic Pro through Adafruit.
Very good. Great.
And Mauser.
Okay. Awesome. All right. Well, thank you very much for spending time with us today.
Well, thank
It's
you for having me on.
been
It's been
fascinating.
a
It's lovely to
pleasure.
hear about your background as well after knowing you for so long.
Yeah.
Yeah. Thank you very much.
Oh,
Um,
I've actually just remembered the other one that I was going to shout out. There's another one project that is on the horizon at the moment, which I've been working on, and that is Mangrove.
okay.
Some of the community might be aware I have been writing a programming language for the last 6 years, including the 4-year hiatus. Actually, nearer 7 now. And so yeah, stick around for streams. I stream every Saturday that I am able. At the moment, it's
Yeah.
been a bit patchy because of sleep cycle and the difficulties of living back with the parents. But I try as best I can to stream every Saturday, and this has been one of the projects I've been working on as well. So
Cool.
you get that to look forward to.
Yeah. Your Twitch link is in the video description, so
Yes.
please feel free to go digging. Yeah. Okay. Brilliant. Well, thank you very much again.
Yeah.
That's going to be goodbye from us. No stream next week from me, but on the 22nd of November, we're talking to Liz Clark, aka Blitz City DIY. So I look forward to seeing you all then. Thank you. Bye bye.
Nice.